Yeah, so it's a great pleasure to welcome Dr. Roychowdhury from Stockholm University, Sweden. So I know Krishanu for quite some time now. So we have overlapped in Max Planck for 2 years, I guess, or close to 2 years, 1.5 years most likely. He's a great friend. So he did his PhD in Max Planck Institute for Complex System in Dresden, in Germany. Then he went from Dresden to Cornell. In Cornell, he was there for a few years, I think 3 years around. Krishanu has been in Cornell. And after Cornell, he moved back to Stockholm University on the last year. And he's been a great expert on non-equilibrium dynamics, topology, and things like that. So he did his PhD with Frank Pohlmann, who moved from Dresden to Munich right now, I think. Good. So today, Krishanu is going to talk about dynamics and correlation in quantum phase transition. So this is his very recent work in collaboration with people from ISCS Kolkata. And I welcome you, Krishanu. Thank you for agreeing to give a talk. Yeah. And usually we interrupt in between for questions. Hope it is okay with you.
Yeah.
Go ahead. Thank you very much again for accepting our invitation.
So thanks, Shomo, for inviting me and giving me the opportunity to give this talk. And it's a very recent work which I have done in collaboration with Rodriguez Moischner from PKS Dresden. Am I audible, by the way?
Yes, you are audible. Yeah,
okay.
Perfectly fine.
And Arnav Dash, who is in Cultivation of Science in Kolkata. And the talk is the work is about dynamics and correlations at a quantum phase transitions beyond Kibble-Zurek. So I will introduce all the elements in my story one after one, and you will find the details of the work in this archive. Yes. Okay, so here goes the outline of my talk. So first I will give you a brief account of what I mean by topological defects, particularly in context of early universe. So the idea of topological defects has been known for a long time. Then I will come to the Kibble-Zurek mechanisms, which applies for defect formation in a quantum phase transition. I will give you the details of this mechanism and the particular approximation which it is based on. The approximation is called adiabatic-impulse approximation. I will tell you the details of the approximation, and then I will give you an example of I will give you an example system in which we will study dynamics between these defects, the correlation between the defects, and we will show that why these correlations needs an these new correlations between defects needs an explanation is beyond the Kibble-Zurek mechanism or the adiabatic-impulse approximation. I will tell you that how you can construct a GG which predicts these correlations, which are very simple at late times. And finally, there are certain elements in our theory which match with KZ, like the Kibble-Zurek thing. I will also highlight those. So basically, this is certainly not in contradiction with KZ, but rather it augments Kibble-Zurek approximations with certain features. And it particularly tells us that this impulse approximation is a rather crude approximation. One should think beyond this impulse approximation if certain observables are studied. Okay, so let me start with the idea of topological defects, which has long been known since the theory of early universe, expansion of early universe, particularly put forward by Tom Kibble around 1976. This is so what he he said that we have when during the expansion of early universe, quantum phase transitions occurred at multiple energy scales. So you can describe this phase transition in terms of a 5-4 theory involving a Higgs field. So you can see this.
So Krishanu, there is a little bit of issue with the internet connection. Is there any possibility that it can be improved? Or
Unfortunately, not from my end, because I absolutely do not have any access to a wired connection. So I'm totally relying on Wi-Fi.
Okay, so let's continue. It's not a big problem, but there is a little bit of a issue, like sometimes it's stopping and then again starting, but it's okay. Let's continue. What else we can do?
Let me actually stop a few applications and then probably it might. Okay. Yes. So, so what I was saying is that so basically the theory of this early universe, what Higgs put forward, what Tom Kibble put forward is the following: is that the dynamics of Higgs field can be described by in a 5-fold theory, which has a potential which is called this thermal Coleman-Weinberg potential. So what basically happened is that in the very early stages, there was everything was very symmetric, and later, as quantum transition took place at multiple energy scales, the symmetry was spontaneously broken at multiple levels, and because of this symmetry breaking, the Higgs field had to choose a particular orientation and a vacuum expectation value, and it gained mass in the process. So a symmetry broken phase is characterized by a finite vacuum expectation value of this Higgs field, while this is zero in the symmetry unbroken phase. But then since initially there was no particular orientations of the Higgs field, the expectation value is zero. When following these quantum phase transitions, domains of uniform orientation and particularly domains of uniform orientations of the Higgs field took place. So we ended up with multiple domains. In each domain, the Higgs field is uniform. However, it is not correlated with the neighboring domains. I mean, not all neighboring domains. For example, domains which formed very far apart, they were not related. So basically, it's the same picture what we see when we look at ferromagnetism. That we also when a ferromagnet is formed from a paramagnet by tuning certain parameter or simply cooling down, we see that around the transition point, uniform. So multiple domains on each domains has uniform magnetizations. However, that magnetization differs in different domains. And you get a correlation length associated with this zigzag pattern, and that correlation length is roughly that correlation length roughly sets the domain size. So if I summarize it in terms of this transition in the language of phase transition, we know that these are all continuous phase transitions, and we know that continuous phase transitions is associated with the spontaneous breaking of some symmetry, which was first postulated by Landau. So basically, what happens is that higher temperatures, when the temperature is much higher than the critical temperature, the system is dictated by a symmetry group, and that symmetry group is broken as the system moves in a lower temperature, which is lower than the critical temperature. And then, so what you see that a group which is, for example, a group which describes the system, I call it G here. That G is broken to, for example, H at low temperature. And now, if the coset space of this G over H has non-trivial homotopy groups, then we see that we have topologically stable defects in the system. These are energetically stable, basically. And you can have different types of defects in the system. It can be domain walls. For example, if it is a discrete symmetry broken, it could be domain walls. It could be strings around which you can have non-trivial winding. It could be monopoles, depending on what type of homotopy groups has a non-trivial value. What type of homotopy groups of these concepts have non-trivial value. So these are basically different forms of topological defects, which was conceived by Kibble, and these defects and populated the early universe. So what Kibble did, that he identified these defects, some of these defects, particularly these cosmic strings, as to be the same as vortex lines in helium-4. And he furthered these idea and also said that the genesis of defects heavily rely on the protocol of the quench. So for example, when a particular parameter was being tuned in a phase transitions, it could be classical, it could be quantum. You can have a linear, the parameter could be tuned in a linear way or in a non-linear way. So that gives you different protocols of the quench. So I call it a quench, tuning the parameter. And what Zurek did, that he sort of gave us an estimate of the density of these topological defects with respect to this different quench protocol. So if there is a rate, if a quench has a particular rate, it could be a linear or non-linear, but if you can associate a time scale with the changing of the parameter, then you can actually prove that the density of defects follows certain scale with respect to this time. Particularly, for example, if I call this parameter, let's say G is a parameter which is being tuned when a quantum phase transition is traversed, then you can see that with respect to these dimensionless parameters epsilon, the density of defects follows this particular scaling, which is this tau q to the minus d nu over 1 plus nu z. This is pretty universal because d is just the dimension and nu is the scaling of the correlation length with respect to this parameter, and z is the dynamical exponent. Sorry, was there a question?
No, I don't see any question as this
Okay,
point.
yeah. So please feel free to stop me whenever there is a question.
Sure. Yeah.
So this particular scaling which I showed here is applicable for a linear quench where this epsilon is linearly tuned with respect to the time. If you have a nonlinear quench, for example, your epsilon is a power of t over tau q, some power, then that power would enter the scaling. Apart from that, it's universal.
So I have a question, Krishanu. So here,
sure.
when you talk about this quench and all of these things, you are talking about a quench which traverses the quantum phase transition, right? So you go across the phase transition.
Yeah, exactly. Yeah, I mean, this in principle applies for classical phase transitions as well. But yeah, I mean, if you just, yeah, exactly. So the parameter is being tuned across the phase transition point.
And then the question is how slow or how fast you are doing it.
Exactly. That would basically change the tau q itself. So the tau, if for a very slow, yeah.
Yeah, just one small thing. So here it is linear. You mentioned once that there can be a linear and a non-linear quench.
Yes.
But even a non-linear quench can be fast or slow. Does it?
Yeah,
Kibble-Zurek depends. I mean,
for example, yeah.
Does Kibble-Zurek depends on this kind of things?
No, the thing is that the fast or slow is entirely captured by this tau q. So if you have a low tau q, it is very fast quench. If you have a high tau q, then it's a slow quench.
I see.
Whether it's a linear or non-linear, that depends on whether your epsilon is a linear function of t over tau q, or it's a non-linear function of t over tau q. Okay. So for example, if it's a simple non-linear function like a power law, so your epsilon could be t over tau q to the r, and then that r, that coefficient, these exponent r would enter your scaling. Then your defect density would be tau q to the power a new exponent which captures r, but the slowness or the highness is still captured in tau q.
So there is a question by Sumiran. Sumiran, go ahead and ask the question.
Yeah.
Sorry, can you hear me now?
Yes.
Yeah.
So this defect density scaling, I suppose that is the ND relation, right? ND.
Yeah.
So is this like in any direction I go from the ordered side to the disordered side or vice versa, I see the same kind of thing? I mean, how should I think about that?
Yeah, I think I will come to that in my next few slides. I hope I will be able to tell you how you get that.
Okay.
And then if not, please ask me again, and then I will try to give you the
But
answer.
right now I should think of it as I'm going from ordered side to disordered side.
You can do the otherwise as well. The thing is that, yeah, I think when I will describe this adiabatic impulse picture, you will realize that how you get these defects and what exactly are the defects, for example.
Okay.
I think that will be clear in my in the go exactly.
Well, in the transverse field Ising model, there's a duality, so I can think both ways, I
Yeah,
suppose.
exactly. You can think of both sides.
Ah,
Exactly.
I
Yeah.
see. Okay.
So yeah, that holds.
Thank you.
Um, So yeah, I mean, in order to talk about, so one quick comment is that in order, if I want to talk about defects, I must specify that what is my order parameter, because the defects are the defects of order parameter. So once you identify the order parameter, it's easier for you to identify the defects, and you will see that
I
what
see.
type of defects are being formed and what is the scaling of that defect.
I see. You have to make precise what the defect is, and then generically such a
Yeah.
scaling applies.
Yeah. Typically, it's assumed that the defects are from where a high symmetry group is broken to low symmetry groups, and
Correct.
then the cos, because otherwise you see otherwise I think the coset space, the homotopy groups are trivial, so you really don't get the topological defects or something. You might get defects, but that will be washed away, I think. Yeah, and then because of this coarsening, etc.
Okay. Thanks.
Okay, so the Kibble-Zurek mechanism is actually based on an approximation which is called this adiabatic-impulse approximation. So it's in a very simple footing, it's a tale of two competing time scales. So you have one time which is called the relaxation time. So if you change a parameter, how the system relax or how the system react to that change. And then there is another time which is called quench time. For example, this is something which Shomo was asking, that for a generic quench, I can, for example, associate a quench time with this formula. So this way I can associate a rate with rate to the quench. So I have basically two different time scales. One is the relaxation time, and the other is the quench time. So quench time is more like in my hands. So I change the parameter, and the relaxation is a system specific thing, how the system reacts. So close to the phase transition point, I can roughly, and also away from the phase transition point, in the entire thing, I can roughly split the entire picture in three stages. When the system is very far away from the phase transition point, if you tune parameters, the system will follow, because the quench time is much larger than the relaxation time. The system will anyway relax if you change the parameter. However, if you when you approach the phase transition point, at some point, the relaxation time is supposed to diverge. And that's given by this power law. And then it will exceed this quench time, because the quench time is linear. You can see in the plot that the red thing is the quench time. So it's changing linearly. Whether the relaxation time is a very nonlinear or a power law. So at some point that the relaxation time would win this competition, and then the system will not be able to relax at all. So no matter what you do in the system will effectively be frozen. And then once you traverse through the phase transitions, and after you go away from the phase transition again, the system will eventually enter the adiabatic stage, and it will start following the change, following these parametric change. So what happens is that, so when you approach the phase transition, at a point where tau r is much greater than tau q, for example, or simply greater than tau q, the system follows the instantaneous state adiabatically. At a point where this tau r is equal to tau q, then you can basically, starting at that point onward, the system cannot relax. So what this impulse approximation does, that the impulse approximation effectively treats the system as frozen, and whatever state you get at that point is just translated to the very other side of the phase transitions, where the tau q will again be equal to tau r. And then after that, the system will again adiabatically continue. So if you equate the expression of tau q and tau r at this point, where t equal to epsilon hat, you basically get the scaling. You can calculate the correlations length at which this mosaic pattern is being formed in the system. And from the correlation length, you can also calculate the density of defects, because density of defects is essentially 1 over correlation length to the power the dimension or the volume. So like I'm assuming that in a volume of which is of the order of correlation length, you have one defect. So this way you can get the scaling of defect once you get the scaling of the correlation. This scaling hypothesis works very well to predict defect densities, and it has been tested in experiments. It has been very accurately computed for certain integrable models. For example, in transverse realizing model, people have computed the density of defects, and the prefactors are also very well known. That prefactor changes from model to model, but the scaling, universal feature of the scaling has been studied thoroughly. And also in these experiments, where they have simulated basically the realizing model, they have also verified the exponent. But now we ask the question that, okay, what if we go beyond this hypothesis, which is the simple scaling hypothesis, and instead of measuring defect densities or the related observable, we attempt to measure the correlations among the defects. There we found that, okay, we get some new results which fall beyond scaling hypothesis. This will be the rest of the talk. Okay, so again, to make this concrete, I focus on a particular example, which is indeed regarded as the fruit fly of quantum phase transition. Is the transverse realizing model, and the Hamiltonian is what you see. It has a ferromagnetic interaction, which is sigma s, sigma x. It has a transverse field, which is linearly tuned with time. The sign of I wrote g equal to minus t over tau q, but this is just to note that initially all spins were like down, where g equal to g is plus infinity, like at the very beginning of the quench. And then I take the quench. One can take the quench to g equal to minus infinity, or one can stop it also, which is the half quench. I will actually specialize to the half quench. But before telling you the details of the quench, let me tell you the phase diagram of the transverse realizing model, which I guess is also very very well known. So you have two critical points at g equal to +1 and -1. Within the critical points, it's ferromagnetic, where sigma x is dominant, and in the rest of the phase diagram, it's paramagnetic. So you can see that the states are roughly like this. So of course, you have the symmetry related states are also there. So this is just our representative state, which I have shown here. So what we do is that we focus on the left side of the phase diagram, basically. So we will perform a half quench, and the quench is from a paramagnetic side to the ferromagnetic side. So that in the ferromagnetic side, we know what is my order parameter, and then I will define defects with respect to that order parameter, and I will see the correlations among these defects, basically. So this is the story of a half quench. So I stop my quench at g equal to 0, exactly when the transverse field is 0. And the defects are then known. Since the order parameter is like all the spins are aligned along these x directions, the defects are domain walls here, and these are energetically stable. So these are topological defects. So for example, these defects, you can still have these defects in the paramagnetic sides, but they are not topological. They are simple kinks. But in ferromagnet, these kinks are actually topological defects because they are energetically stable. So there is an energy associated with the stability of this defect, which is the order of J. And now what I want to do is that I will actually compute the correlations among these defects when the defects are, for example, separated by a distance r. But before going into that, let me give you the, yeah, it's okay. So let me walk you slowly, step by step, like how you solve the system and then how you solve the correlator. So I start with Hamiltonian, and particularly for the defect which I'm interested, I need to introduce dual variables. This is simple Kramer-Svanier duality, which also we are talking about. And then this duality also says that there is a mapping between G to 1 over G. That means the ferromagnet to paramagnet and the otherwise, and the other route. So, but I will calculate everything in terms of these dual variables. So in terms of these dual variables, I get a new Hamiltonian, which I call this dual Hamiltonian. And then then what we do, we do fermionization, basically Jordan-Wigner fermionization. And once you introduce these fermions, you can go to the Fourier space, provided you have I'm dealing with the periodic boundary conditions. I go to the Fourier space, and in that Fourier space, the value of the quasi momentum are decided by the parity sector, because parity is parity commutes to the Hamiltonian, and then whether it's a plus or minus, that will give you that fixes the values of the quasi momentum for you. Okay, so once I have fermions, what I do is that I do a time-dependent degeneracy transformation, where time dependence of the fermions, the original fermions, are entirely encoded in these coefficients UKT and VKT. So I will have to study the time dynamics of these coefficients, basically, because this gamma t, which are the Bogoliubov fermions, they are taken to be constant of motion, because I am calculating things in this Heisenberg picture, where I can essentially treat this Bogoliubov fermion to be frozen. That means my instantaneous state is always a Bogoliubov vacuum. With that setup, I can now solve these time-dependent differential equations. However, it's not straightforward, because it's still a bit complicated, because I have time dependence in the off-diagonal elements. So if I can get rid of the time dependence in the off-diagonal elements, then I can cast this problem in the standard Landau-Zener problem and go on for the solution. So in order to do that, what I do is that I basically apply a unitary transformation, which is the following, and that actually dumps the entire time dependence into the diagonal elements. So now my off-diagonal elements are absolutely free. So there's no time dependence in the off-diagonal elements. And this we can explicitly solve. The details of the solutions, etc., are given in this paper. So I'm not going into the details of the solution here, but this is solvable. And with the solutions, we now attempt to calculate the defect correlations. So as I showed you like a couple of slides back, these are the defects. And so basically I want to calculate, and the way I define the defects is the following. So a defect at a point J, a defect between J and J plus R is given by this operator, which is 1 minus sigma x J plus R, sigma x J plus R plus 1. So for example, if there is no defect, then this is 0. If there is a defect, this is 1. And that's my defect operator. And relations is defined as when I have two such operators separated by distance of R. And this is the form of the connected correlator. So I have subtracted the R goes to infinity limit of the correlator. And now again, in terms of these dual variables, this takes the simple form, which is mu z. And then I can actually do the fermionization, which I was explaining, and then you go to the Bogoliubov fermions, and then you calculate the UK and VK with respect to so you calculate their time dependence. And the rho r, once you replace the expression of mu in terms of C's, and then the expressions of C's in terms of gamma, you get the expression of rho r to be the following.
Krishanu, one small question. What is your initial state and how it enters here?
So my initial states are where, for example, all spins up. I started with
no defect.
G equal, no defect, yeah.
Okay.
Yeah, for example, this initial defect. So yeah, so in the differential equation, when I will solve it such that my uk is, for example, 1 at the very beginning and vk is 0 at each k, because at each k, because it's basically an ensemble of two-level systems at each k. So at each k you set this u to be 1 and v to be 0 to be your initial state.
And another small question. You are
Yeah.
asking about defect correlation, but we do know that there are certain limits where I can stay in one defect subspace. So let's say I created only two defects and I remain in that subspace of the problem, so that there is no correlation or defect generation can also happen, right? So, or am I
Yes,
sounding?
but you have a transverse field that will not let you stay in that space.
Oh, well, there is a limit. Okay, fine.
Oh,
I agree with you. There is one limit where I can always do. So it depends on how you are doing the quench, but you are right. So maybe you are doing the quench across the phase transition.
yeah, exactly.
So
So I'm doing the
that's
quench
probably,
across the phase transition, and then I will stop within deep into the ordered phase.
okay, thank
Mm. Okay, so that's so these are the formal solutions of the Landau-Zener problem. So let me tell you some details of the solution. So for example, you can see that this UK square has a non-trivial dependence on these parameters, which is RK and SK. And basically it is these elements which will set the form of the correlators basically. And you can see that there is a Gaussian nature of these there is a Gaussian nature already coming in this expression. For example, if you approximate it around k equal to 0, you will see that it's Gaussian. And since we have only crossed one critical point where k equal to 0 is always that's the transition point. So I can sort of that k equal to 0 is the point where the gap closes. So I can sort of approximate the entire these quantities around that k equal to 0 point. And around that, these quantities are Gaussian, but it is also, but these expressions also have these phases, these phi k and omega k, and these phases have non-trivial dependence on the time. You can see that these phi k and omega k depend on tau, where tau is linearly proportional to the time t. And since I stop at g equal to 0, there t equal to 0, so my final tau is just tau cosine k. Now, since I'm approximating around k equal to 0, I can take a tau goes to infinity limit, because those are the asymptotes which you can take out of those differential equations. So I can still take the tau goes to infinity limit, provided my tau is very large. So for a slow ramp, I can still move forward and play with these functions. Or also this is this for the half ramp. But for the full ramp, if you start at t equal to minus infinity and go to t equal to plus infinity, these observations also hold even for small tau q, because the asymptotes at time is taken care by the parameter t itself. But for this half ramp, the large asymptotes can only be guaranteed when tau q is very large, because t is 0. So for the slow ramps, we can still get some simplified results. We can still show analytic results. And we found that after doing some simplification, you see that the defect correlators show a very clean Gaussian decay. And also the refactor has a dependence on the tau q. And these are the plot is a summary of the numerical results which we have performed on a chain of length 10 to the 4 and at various tau q. The number which you see, the values of the tau q are set with respect to j, which is taken to be 1 here. So that's how I have normalized the parameters here. So again, for small r, not smaller, I mean, you can see that for a very large r, certainly the numerical results are not very trustworthy, because it hits 0. It goes below the numerical precision. But still, in a limit where these are measurable, you can see that it's very clean Gaussian decay in the defect correlator. Okay, but then after I see that okay, there are Gaussian, and there is a Gaussian decay in the defect correlations when you stop the ramp at the end of the ramp. But is there a signature of Gaussian decay in the eigenstates? I mean, typically what we expect that for quenches, properties which appear at the end of the quenches are already encoded in the eigenstate in some form. It could be a ground state, it could be excited state. But whether there is any signature of Gaussian decay in the eigenstates, that's what we wanted to know. Then when we compute the Gaussian correlation in the eigenstate at a given G, so that's like the static Hamiltonian. So you solve the static Hamiltonian, you compute its eigenstate, and then compute the defect correlations. You see that it has this complicated form in terms of these hypergeometric functions.
Hey,
But you can take as in, yeah.
Just one question. So this
Yeah, sure.
log of that plot you showed, or this
Yeah.
row of R, this is at what, infinite time after the quench, or when, which time?
No, this is right after the quench. I will come to the infinite time results.
So this is right after the quench.
Yeah, this is right after the quench. Exactly. Yeah, this is right after the quench.
Meaning, sorry, at what time in the ramp is this?
You mean what time is the ramp stopped?
No. So I'm doing the ramp, right?
Yeah. Yeah.
And I do the ramp, and then you are measuring at each time of the ramp this correlator, right? Or no?
No. At the end of the ramp. So you measure the states at the end of the ramp, and then you compute the correlator at those states.
Okay, so this is at the end of the ramp.
Exactly. So this is, yeah, exactly. So these are all at the end of the ramp. Yeah. So basically you compute UK and VK at the end of the ramp.
Okay.
And then you compute the correlators by this formula. So then you get the correlators at the end of the ramp. But you can also compute the correlators at each instant of time when you have a static Hamiltonian, for example. So that will give you the correlation functions in the eigenstate as a function of G. And then when we do that, we find that this correlation function has this complicated form, which is in terms of these hypergeometric functions, but you can still simplify that. I mean, you can take asymptotes of these hypergeometric functions. And you see that, for example, if you take R much greater than 1, then you get back the expected exponential decay. That's the naturally expected thing. So basically, you see that eigenstates show exponential decay when you measure the Gaussian correlations. But the ramp.
Sorry, Krishan, when you say eigenstate, you mean the ground state?
Yeah, exactly. I'm also correct. Yeah, exactly. So this is measured in the ground state, for example. Okay. You can also measure it in any eigenstate. You will still get the same form. And also particularly, you can prepare a state, which we call the box eigenstate. So you sort of you excite k modes selectively, for example, up to a particular point, say k star, and beyond k star it's still the ground state, for example. And then in this complicated state or this in this box eigenstate, if you measure the Gaussian, if you measure the defect correlator, you still see that there is Gaussian. Sorry, this is exponential. So in these box eigenstates also, there is no signature of Gaussian. And also if you prepare a random eigenstate by exciting k mode selectively, but that's from a random distribution, you still see there is no signature of Gaussian there. It's pretty random, but the Gaussian signature is no way present in any of those states.
Can you quickly explain why you expect a Gaussian to be in?
No. The thing is that, okay, so why should I? Okay, the reason is that typically in quenches, when you do quenches, the final results, all the properties which you get in the final results, they are already in some form encoded in the initial state which you started with. For example, if you do an instantaneous quench and you measure things after the instantaneous quench, you get exponential behavior, which is already there in the initial states. In your initials, in the gapped phase also, your states show the exponential behavior. And of course, it could be algebraic close to the phase transition point. But all the properties, basically, the state inherits the property from the eigenstates.
Well, more technically, it's the overlap that matters. So overlap with the initial state.
Yeah, sure. But if you calculate that, you will see that there is no Gaussian in any of those states actually.
I see. Okay, thanks.
So Gaussian correlator is a feature of quenches, is it, generically?
Sorry, it's a feature of what? Sorry, I couldn't hear you.
Quench, when you do a quench, because in normal equilibrium situations we never see a Gaussian correlator, right?
Exactly. Yeah, I will come to that point actually.
Okay.
No, but if you, okay, let's continue. Yeah, we have 10,
Uh,
15 minutes. Yeah.
Okay, so what we learned from that Gaussian correlators are simply absent in the eigenstates. So you cannot expect Gaussian correlators in equilibrium states, what Sumiran was sort of telling us. So the properties of these, because as I was saying that typically what you expect is that all the properties of equilibrium state in one side of the phase transition is used to obtain excitations in the other side of the phase. And since no eigenstate show Gaussian correlations, we expect that the dynamics which took place in the impulse regime is actually beyond what is typically is beyond the frozen approximation that your state remains frozen. So there are considerable dynamics around the phase transition point, which goes beyond the impulse approximation. And that's captured in these defect correlations. And that certainly is not present if you measure any other correlations, spin correlations, something. If you still measure spin correlations, you see normal exponential decay, which you expect from the eigenstates or equilibrium state. And then we also, so then this sort of brings to an approximate picture that the defects which are being generated in the process are forming a dilute gas because it's very slow ramp. So your correlation length is very large. Defects are produced very far apart. They are essentially non-interacting and forming dilute gas. And in a dilute bosonic gas, for example, or it's equivalently true for hot fermions as well, you get Gaussian correlations because you are basically dealing with free particles. On the other hand, if you measure spin-spin correlations in the longitudinal direction, like in the sigma x directions, you see that there is a exponential oscillatory decay associated with the spin-spin correlation. So it depends on the rate actually. If you drive it very fast, then you see it's just an exponential decay. But if you drive it very slow, if you drive the ramp very slow, you see that there's an exponential oscillatory decay, and that the wavelength of this exponential correlation is basically that provides the correlations length in the picture. And we so what we found actually is that you can relate these fermionic these spin correlations in terms of the fermions which are present in our theory. And it turns out that these different speed of the ramp can be translated in terms of the occupation probability of the fermions and an effective dispersion. The dispersion depends on the speed of the ramp, and when the ramp is very fast, you see that there is no Fermi points present in the dispersion. Otherwise, if the dispersion is very slow, you always get a couple of Fermi points. So as long as there are Fermi points, you see oscillatory decay. And when there are no Fermi points present, you basically see an exponential decay. So these are the behavior of the fermions. And since these are non-local fermions, if you calculate the correlation function, you will see that there is a Peptid's determinant present in the system, in the expression. And no matter how fast your speed, how fast your ramp is, it can never be Gaussian. So that's again in contrast with defects. So for example, defects behave like free particles. On the other hand, these fermions are sort of non-local fermions, and they can never behave like a free particles because the strings are always present. So it's always exponential or the oscillatory exponential. So that's kind of and these fermions never show a Gaussian decay. It is only the defects which are local and they show the Gaussian decay. So having said that, we also analyzed what happens at the late time. So for example, if you really wait for a long time after the ramp has ended, you see that you still get Gaussian correlations. So these Gaussian correlations get stable at the long time limit. So what we we then ask that whether there is a GGE, there is a generalized Gibbs ensemble which can predict these Gaussian correlations, because we know that such an integrable system will anyway run into a GGE at one point, and all the properties will be dictated by that generalized Gibbs ensemble. So then we found that if we construct a generalized Gibbs ensemble for this problem and measure the correlators in this ensemble, or with respect to this density matrix, we see that essentially this density matrix is product of these Lagrange's multipliers which are there in lambda k. And lambda k actually explicitly depends on both the initial states and the final states. It actually depends on the overlap of those states. Since this final state is very non-trivial for a ramp, in contrast to a direct quench or an instantaneous quench, if you have a ramp, this final state is very non-trivial. That's what is supplying the Gaussian nature to the GGE. So if you if you construct the GGE explicitly by calculating these Lagrange multipliers, and then you calculate the correlations, you still see that you get the same Gaussian correlations which you get from just by weighting long time limit. So when I say just by weighting long time limit, what I do is that it tests the ramp, then you can evolve the system with respect to a static Hamiltonian, which is frozen at that point of time, and then you can calculate the correlations as t goes to infinity. So if you do that, you get the same results as the GGE. So that basically says you can still get these Gaussian correlations in a GGE, and which is also expected because it's stable at late times. And this is certainly very different when you have an instantaneous quench or a direct quench, because in direct quench what happens is you essentially get you get the eigenstate behavior back. So you see that if you do a direct quench and compute these correlations, you get exponential. And from the dilute gas picture which we put forward, what instantaneous quench does, it produces a lot of defects in the system. And then the defects cannot remain far apart or non-interacting. So they are now interacting defects. And then once you have interactions switched on in your game, the Gaussians you get your Gaussian gets washed away, and and then a conventional or expected exponential feature sets in. So for an instantaneous quench, if you calculate these defect correlations, you'll see it's exponential in either side of the phase transition. So for example, G equal to 1.5 is in the magnetic side, where 0.5 is in the ferromagnetic side. You can see an exponential decay, and you also see the exponential decay when I reverse the instantaneous quench. So there we expect not to see any Gaussian. Okay. So now what happens if we sort of move out of this integrability a bit? Since integrability is really not an issue in these Gaussian correlators, we expect that, of course, in non-integrable system, Kibble-Zurek predicts the thermal, so you get the temperature which is predicted by Kibble-Zurek at long times in general non-integrable system. And there our picture also qualitatively agrees with Kibble-Zurek. However, at short times, in non-integrable system, Kibble-Zurek will not be able to predict Gaussian decay, even though we expect those Gaussian decay to come up right after the end of the ramp, even in non-integrable system. So that's sort of, we are working on that to show that how you can still expect Gaussian decay in non-integrable systems right after the ramp. Of course, at long times, this will be washed away, and then your usual exponential will set in. So that's consistent with the Kibble-Zurek picture again. So it's not really limited to this non-integral model. To some extent, it also goes on this integrability issue. And we expect to see Gaussian at short time in non-integral systems. Okay. But still in our picture, we see that there are certain time scales and length scale associated with the onset of this Gaussian behavior, which matches well with the Kibble-Zurek approximation, with the Kibble-Zurek scaling hypothesis. Particularly, what we do that we try to probe that when does the Gaussian behavior sort of take place, like traverse the quantum phase transition point. In order to do that, we probe it in very fine state close to the phase transition point. And what we measure is the correlation coefficient of the Gaussian plot. And we see that the correlation coefficient, if the correlation coefficient is close to 1, that's like perfectly correlated. So if it's away from 1, that's like your the data is not so correlated. So we measure this correlation coefficient for the Gaussian data, which is given in this data set. And then we see that, of course, away from the phase transition point, there was no Gaussian, it was eigenstate behavior. So R should be away from 1. But as we are approaching the phase transition point and we go past the phase transition point, we see that R gradually, there is an oscillatory behavior in R, and then it gradually goes to 0. That means Gaussian behavior is setting in. So if we now locate these extrema in this behavior and then measure these extrema with respect to tau q, we see that the time scale reveals the expected Kibble-Zurek scaling, which is tau q to the -12. So time scale for the onset of this Gaussian decay still has Kibble-Zurek scaling. So our picture is in that sense consistent with the Kibble-Zurek mechanism. And also we should expect that in the near time experimental there is a near time experimental real. So basically this theory is very viable in real experiments. For example, the experiments which I showed you in the beginning, in these Rydberg experiments, they can measure these correlations at this scale. So for example, short time, if you measure correlations and defect correlations at short R, you will still be able to see the Gaussian relation. So that's sort of experimentally, I would say, testifiable. Yeah, with this, I would like to conclude. So what we have learned in this work is that, of course, if you measure these Gaussian correlations in the system, the adiabatic-impulse approximation fails to predict the nature. It cannot explain why you should expect Gaussian for a ramp. So that means that there is a considerable dynamics taking place in the impulse regime. So this frozen approximation is not correct. One needs to go beyond this frozen approximation, which is this impulse approximation. And also we see that these defects are like classical particles showing Gaussian behavior, and the length scale and time scales associated with our theory matches with the standard Kibble-Zurek approximation. So in this sense, it is not contradicting KZ, but sort of augmenting KZ and asking it to be revisited, particularly from the dynamics perspective in the impulse regime. Yeah, with this, I would like to conclude, and thanks everyone for your attention.
Thank you very much, Krishna, for this nice, interesting talk about Kibble-Zurek mechanism. So is there any question? It seems there's not immediate question, so let me ask then some of the things. So first of all, I do understand the math, why it should be Gaussian and not something else. But do you understand what really leads to this Gaussian correlation? So is there any physical mechanism that you can tell us that?
No, actually, yeah, I think no. I mean, the short answer is no, because we really do not know the details of the dynamics in that impulse regime. So only the approximation which exists is this impulse approximation, where you basically treat the state to be frozen. Of course, you cannot take that to be frozen. So somehow some other non-trivial higher order approximations need to be done there. But otherwise, the reason for which we expect this Gaussian is only the state which is produced after the ramp, the very complicated state. And that is, so, and the Gaussian behavior is basically encoded in that state. So your UK and VK after the ramp has Gaussian behavior. So if your quench protocol is such that the state at which you end up has these very complicated features, then I expect that you will also see Gaussian behavior in those states. So that's why this ramp thing is very distinct from the instantaneous quench. And this impulse regime is basically instantaneous quench. When you do this impulse approximation, you are basically doing an instantaneous quench. And that's not sufficient, yeah.
So when you say instantaneous quench, you mean that it's
a direct
fast.
quench. Exactly,
Fast.
exactly. It's a very fast quench. So your tau q is sort of zero. Tau q is
yes.
zero. Yeah.
And then you would expect that this thing to hold.
Yeah, exactly. So if you can modify the impulse approximation somehow, it could be a linear approximation, for example. It could be a non-linear approximation, but it has to be something which is not just the approximation which is there now. It cannot be instantaneous quench. It has to be something else than that.
Okay. So I have another question. So usually I always see that this Kibble-Zurek and all these things, you do the quench across the transition. That's okay, makes sense. But what happens if I stop at the transition?
Yeah, I think there are already work. You can, yeah, I think there are already work where, for example, I think there are work by Krishnendu and others, and a few others where they have stopped at the quench and they have measured, they have got some algebraic features there, both algebraic and exponential features, depending on where exactly you are stopping. Yeah, that's, I think there is, yeah. So there are work where people have done that, but we haven't done that. We haven't measured the correlators when you have stopped at the quench.
So when you measure this defect correlation, it is essentially you are asking how the defect moves, right? So this is more or less
yes, yeah,
movement
or
the dynamics of the defects.
Exactly. How the domain size are changing, and then how different domains are, how basically you are approaching in a uniform state in the other side of the phase transition.
Nice.
Yeah, I mean, what we basically do is that typically if you measure other observables like spin correlations, you just see that, okay, whatever is there in the eigenstates, you are just getting those behavior. Even if you do a ramp, you measure the spin correlations, you see that it is exponential. You measure these like longitudinal spin correlations, you see that it's exponential. So okay, so then I expect that from the eigenstate. But if I measure these defect correlations, I see that it's Gaussian, which I don't expect from the eigenstate. So that's kind of one observable which we found, but I'm pretty sure there would be other related observables in which you will see similar signatures.
Okay, and the answer to your non-integrable thing, I did not really fully understand. So if you have a non-integrable field,
so we have dealt with an integrable model.
Right.
And for non-integrable model, you expect a thermal state at long time. So it will thermalize. And then this temperature is predicted by Kibble-Zurek mechanisms, and people have done that. So Kibble-Zurek holds for non-integrable system. However, if you stop right after the ramp, in Kibble-Zurek cannot predict whether there will be a Gaussian or not. But we expect that this Gaussian would show up in non-integrable systems as well at very short times, because integrability is not an issue here at all.
Yes.
But then at some point of time, it will be a crossover to an exponential, which is expected for non-integrable systems. But we still expect to see Gaussian to come up at short time scales in non-integrable systems also.
Okay.
That's what Kibble-Zurek cannot predict.
I see. Yeah. Good. I think I don't have any more questions, so I can, and there is none in the YouTube. So I would like to thank Krishanu again for giving this nice overview talk on the Kibble-Zurek and on your work. And also would like to thank all of the the participants in the Zoom as well as in the YouTube for joining for this nice talk. Thank you very much, Krishanu.
Okay, Shomo.
Yeah.
I have a question. Small question.
Okay, go ahead.
So so it was connected to Shomo's question. So is there any other context in which such exponential correlations have been seen in some observable? Like, can I write down an eigenstate, a quantum state, where can I cook up a quantum state with exponential correlations?
Exponential correlations of what? For example, if you measure
your Gaussian correlations.
I mean, if you measure spin correlation, you will see not usual exponential.
Sorry, Gaussian correlations. I didn't mean
Yeah, he made Gaussian.
No, that's what we found. I cannot cook up a state in which it is Gaussian.
So it's really some complicated state, and you
Yeah, exactly.
that's very strange because Gaussians are generally a sort of a central limit theorem type of probability distribution. Like it hints that there is some sort of something like that might be at play. No?
True, but no, I understand. I agree with you exactly. So it comes from the central limit thing. For example, yeah, I mean, if you study these random walk problems, etc., you know that there are Gaussians in the time distribution, etc. But spatial Gaussian is something which I think a little more exclusive than the temporal one.
Okay.
Of course, in diffusions, etc., you expect Gaussians in temporal Gaussian, but spatial Gaussian is in that sense is a bit special.
And one small question. So I saw in some of your plots, your log rho of R was -60 and stuff. And so that is just a sort of numerical evaluation of.
Yeah, exactly. Yeah. I mean, if you go beyond that, you basically fall out of the numerical precision, and then that's not sort of
I see.
trustworthy.
So it's like some hypergeometric functions you are evaluating in the computer.
Yeah, in the exact case, yes, exactly. I'm calculating that hypergeometric functions.
And
It's
they
just a
can be
mathematical.
computed to almost like machine precision.
Yeah.
Right. Okay, nice.
Okay.